asymptotes, and it's about vertical and horizontal asymptotes, and it's limits involving infinity, either when the answer is infinity or as your number approaches infinity. So my objective is related to limits. You can deduce and interpret behavior of a function using limits, and that's the asymptote behavior, and we're also going to find limits of functions. So we're going to look at asymptotes first. So what I'd have you do in class is I'd have you graph this function on your calculator or on Desmos. I want you to note that if you're going to use your calculator to graph it, the way you get an absolute value bar in your calculator is you type ABS, and then you would do an X inside of the parentheses for ABS. That's the absolute value function for your calculator. On Desmos, you can just find that on the keyboard. It's right above Enter. So try graphing it, take a look at it, pause the video, and come back after you've seen the function. Think about the asymptotes as you're looking at that graph. Maybe zoom in and out so you can think about the asymptotes. All right, so I graphed that function on Desmos, and what I notice is that there looks to be an asymptote right around here and a different asymptote here. So it has two different horizontal asymptotes. What I also notice about this function, which you may be surprised about or maybe not, is that the function crosses that vertical asymptote. So you see it cross that, horizontal asymptote. So that may or may not surprise you depending on what your teachers in the past have told you about asymptotes. But it is okay for a function to cross an asymptote. That's not a violation of any rule. And then there's looks like a vertical asymptote right around here. So just looking at the graph, I do see that it has two horizontal asymptotes and a vertical asymptote. Okay, so we're going to start with vertical asymptotes. Vertical asymptotes are zeros in the denominator that don't factor away. When we've been studying limits, we have been factoring away zeros in the denominator when we get something like 0 over 0. So for these problems, for vertical asymptotes, you're going to have some number that's not 0 over 0, and that's when you know you'll have a vertical asymptote. The limits as x approaches vertical asymptotes are going to be positive or negative infinity, and your main job when you're looking at those limits is to decide which one it is, whether it's positive or negative infinity, or whether as x approaches that vertical asymptote from both directions, the infinities might be different as well. So if I'm looking at this function, I'm trying to find a vertical asymptote for this function. I sort of look at the numerator because I want to pay attention to whether my 0 in the denominator will cancel, but I'm mostly looking at the denominator. So I have 2x minus 6. That's going to be equal to 0 when x is equal to 3. Or you could have also factored it as 2 times x minus 3. So you would see x equals 3 is going to be your vertical asymptote. I can tell just by a little bit of examination that x equals 3, that x minus 3 wouldn't cancel in the numerator. So x equals 3 is going to be a vertical asymptote. Also, you could notice that if you plug in 3, you would get 29 divided by 0. And so that's not going to be a factorable 0 that you can get rid of. So you have a vertical asymptote at x equals 3 for this function. Sometimes on homework you're going to be asked to examine the behavior to the left and the right of a vertical asymptote. So the way you do that is you take the limit as x approaches 3 from the negative direction and the limit as x approaches 3 from the positive direction for your function. And we know right away, because it's an asymptote, we know that our answer is going to be some kind of infinity for both of these two limits. We just don't know whether it's going to be positive or negative infinity. So what I really am caring about when I look for these limits is I just care about signs, because I just want to decide whether my answer would be positive or negative. I already know it's infinity. So I go to a little number, a number that's just a tiny bit smaller than 3, and I'm not actually even thinking of a number. I'm just thinking, okay, tiny bit smaller than 3. So this would be around 30. 30 minus 1 would be a positive number. Okay. A little bit smaller than 3 times 2 would be a little bit smaller than 6. A little bit smaller than 6 minus 6 would be a negative number. So I'm taking a positive number divided by a negative number, so I know that this would be a negative infinity. And then if I go a little bit bigger than 3, I'm going to have a number around 30, 29 again, and that would be a positive number. And then a little bit bigger than 3 times 2 would be a little bit bigger than 6. Minus 6 would be positive. So this one would be a positive infinity. Just like before when we noticed that these two don't match, they're different kinds of infinity. If I want to talk about the limit as x approaches 3 of this particular function, I would have to say it does not exist. I wouldn't say that it's infinity or negative infinity. If I'm just approaching 3, I would say it does not exist because the two types of infinity don't match. If they were the same type of infinity, I could say that that's the limit as x approaches 3 for that function. Oh, I'm going to back up a little bit. So just if you're thinking about this, if you're just kind of roughly thinking about a graph, as x approaches 3 from the negative direction, I don't really know what's going on, but I do know that my graph is shooting down towards negative infinity, and as x approaches 3 from the positive direction, it's shooting up towards positive infinity. Okay. You can also think about horizontal asymptotes for a function. I want you to be aware that a function can have 2 horizontal asymptotes at the most. Could have 0 or 1, but it can't have more than 2 because the definition of a horizontal asymptote is it's the limit as x approaches infinity for a function and the limit as x approaches negative infinity, and so you could only possibly have 2 different answers for that. You might have the same answer, you might have no answer, they might both be infinity, in which case you don't have any asymptotes. So the way you're going to evaluate those limits is you're going to use end behavior or dominant terms to evaluate limits as x goes to infinity. The way you decide what a dominant term is, first you want to look at any exponential functions you have. You may not use them, but you need to think about them first. Remember that e to the x grows super fast. It starts off very small and it grows super fast. So as x goes to infinity, e to the x is really dominant. But as x goes to negative infinity, e to the x is not dominant. So I would use e to the x if I'm doing a limit as x goes to positive infinity. I would not use e to the x as x goes to negative infinity. E to the negative x is backwards from that. E to the negative x is exponential decay, starts off huge, gets very, very small. So if I'm evaluating a limit as x goes to positive infinity, I'm going to ignore e to the negative x because it's not a dominant term as x goes to positive infinity, but I would use e to the negative x as x goes to negative infinity because that function is really impacting my function a lot in the negative direction. Once I've thought about exponentials, then I choose the highest degree of x that I have, ignoring all other x terms because they don't really have any impact beyond the highest degree. One note, if you have any absolute value functions within your function, you're going to want to write that as a piecewise function so that you can think about it in both directions in pieces. What I mean by that is we write absolute value of x, but what we really mean when we write that is we mean that our function is 2 pieces. It is just plain old x as long as x is bigger than or equal to 0, but it's the opposite of x if x is already negative. Okay, so if I want to look at horizontal asymptotes of this function that we looked at before, the first thing I should do is write it as a piecewise function. So in 2 pieces, this would be 10x minus 1 over 2x minus 6, and that's as long as x is bigger than or equal to 0. But if x is less than 0, it's going to be 10 times the opposite of x, minus 1, over 2x minus 6. Now that I've gotten rid of the absolute value so I don't have to think about that as something different, I'm going to look at the limit as x approaches infinity for f of x, and now I'm going to look at dominant terms. So the minus 1 has much less impact than the 10x, so 10x, and the reason I'm using this part of the definition is because my x is going to positive infinity. So that's going to be 10x as dominant term in the numerator and 2x as a dominant term in the denominator. And so then I can reduce that because the x's can cancel to just 5. So I have a horizontal asymptote at y equals 5. I can do the same thing as x goes to negative infinity. As x goes to negative infinity, I would use this part of the definition. And so that means that the dominant term would be negative 10x over 2x, which would be negative 5. So I have a horizontal asymptote at y equals negative 5. And that's what we saw when we graphed it, but that's now we've examined how you would find that without relying on technology. All right, so we're going to just look at one other function in class, and then there will be some homework problems as well. So if I'm looking at vertical asymptotes, remember vertical asymptotes are zeros in the denominator that don't factor away. So I'm going to start this process by factoring everything I can. So I notice that this numerator would be x plus 2 times x plus 1, and the denominator would be 2x plus 3 times 2x minus 3. Technically, I didn't have to factor the numerator, but I wanted to make sure that the zeros I found in the denominator weren't going to cancel out. So now my vertical asymptotes are going to be x equals 3 halves, negative 3 halves, and x equals positive 3 halves. So I have two vertical asymptotes to look at. And then I might want to look at the behavior of the function in both directions. So if I choose a number a little bit smaller than 3 halves, well, the numerator would definitely be a positive number because I'm adding 2 times a positive number because I'm adding 1. The denominator would be, if I'm a little bit smaller than 3 halves, 2 times something a little bit smaller than 3 halves would be a little bit smaller than 3. So this would be, it would still be positive because everything is positive in that term. But this one would be negative because I'm a little bit smaller than 3, and then I'm going to subtract 3. So this one would be I know it's infinity because it's an asymptote, but it would be a negative infinity. So if I keep following that process, this one would evaluate to a positive infinity. And then if I'm at negative 3 halves and a little bit smaller than that, definitely my numerator would still be positive because it would be negative 3 halves plus 2. Oh wait, maybe that's not true. So negative 3 halves plus 2 would be a negative. Negative 3 halves plus 1 would still be a negative. So it would be a negative times a negative. No, negative 3 halves plus 2 would be positive. And then negative 3 halves times 2 would be a little bit smaller than negative 3 halves, so it would be negative. And then this would be negative. So I've got negative infinity. And then by the same logic, if I'm approaching negative 3 halves from the positive direction, that graph would be going down towards infinity. Up towards infinity. Down towards negative infinity, up towards positive infinity. If I want to look at horizontal asymptotes, again, I'm going to look at dominant terms. I'm going to look at end behavior. So this would be x squared over 4x squared, so that would be 1/4. So I have a horizontal asymptote at y equals 1/4. And same thing for negative infinity. So I just have one horizontal asymptote for this particular function. So a summary, vertical asymptotes are zeros that don't factor out of the denominator. The limit at vertical asymptotes is either infinity, negative infinity, or does not exist if the two types of infinity don't match. Horizontal asymptotes are the end behavior of a function, and the limits as x approaches positive and negative infinity are called the horizontal asymptotes.